All right, hello everyone. This is Dr. Gallenstein, and today we are doing lecture number 7. In lecture number 7, we're going to continue our discussion. We're going to continue our series in which we are talking about the assumptions of the ordinary least squares approach to estimating regression coefficients and the various issues that can arise when some of those assumptions do not hold. Today will be the last lecture in that series. We're going to talk about a problem called heteroskedasticity. It is an incredible mouthful. Heteroskedasticity. Heteroskedasticity. We're going to talk about a problem called heteroskedasticity. What is it? What problem does it cause? And then how do we solve it? And how do we figure out whether or not we have it? We're going to do all of that today. We're also going to start with a review of F-tests and when we would use that test, and then how do we actually calculate it. Before we kind of did it conceptually and we did it in Stata, but today we're going to do it by hand. I'm going to show you how to produce an F-statistic. I'm going to show you how to test a hypothesis using the F-test. All right, so we're going to do that first. Then we're going to get into heteroskedasticity, and then, as is the usual, I will demo everything using Stata. All right, so without further ado, let us begin. Lecture number 7, heteroskedasticity. All right, F-test first. Now you'll see we're going to use the F-test later in the lecture, so it kind of synergizes. All right, so remember our example. In the example that we used a couple lectures ago, we talked about a model that would, a model for what the determinants of a student's GPA, okay? And we said that, okay, a student's GPA is a function of the instructional format of the courses that the student takes. So, the percentage of the classes that they take in kind of a traditional lecture format versus the percentage of classes that they take in an online format, okay, as well as the number of hours, that they spend studying, and their major, so their university major. All right, so we're saying that the student's GPA is a function of these 4 things, and the other things are all captured in the R-term. All right, now when we look at a model like this, sometimes we might want to do a joint test. Now we can do hypothesis testing on each of those coefficients separately, and that's what we always do when we run regressions. Every time we run a regression, we do a hypothesis test on each of the coefficients to see whether or not we can conclude that that coefficient is different from 0, right? So we always do the null hypothesis is that the coefficient, the estimated coefficient on any of the variables is actually 0. And that's our null hypothesis. And then we will reject that null hypothesis if if our t-statistic using a t-test is large enough, right? Okay, but now sometimes we might want to do a joint test. We might want to do a joint test. That's where we want to test if multiple variables are jointly significant. Okay, now there can be a number of different reasons why we would do this, but let's go through one of those here in this lecture. Okay, so what you'll see in this example is that these 2 variables, lecture and online, these 2 variables are both examples of instructional formats. And there's other types of instructional formats, but these are 2 examples of instructional format. All right, and then these are other determinants, hours spent studying and major. When we look at this, we might say, okay, I'm interested in whether or not the lecture format affects GPA, and I'm interested whether or not the online format affects GPA. But I might be interested in asking myself the question of whether or not the instructional format matters at all. See, these are both examples of instructional format. I might be interested in whether or not instructional format matters at all. And if I am, I might want to do a joint test to see if these two are jointly significant. Now, if they're both separate, if they're both significant separately, then we don't necessarily need to do the joint test, because they're going to be jointly significant if they're both significant. But so let's assume one of them is significant, one of them is not. In that case, we might want to do a joint test where we want to see, does the classroom instruction matter at all? Does the group of a classroom instruction matter? Okay, so once we've controlled for so perhaps this is the case. Perhaps once we have controlled for the number of hours that the students spend studying, and we control for their major, perhaps the format of instruction, whether it's an in-class lecture or an online course, perhaps the course of instruction doesn't matter at all once we control for the hours spent studying and the student's major. Well, the way that we would test that would be to do a joint test where we state the null hypothesis that beta 1 and beta 2 are both equal to 0. And then the alternative hypothesis that the null is false. All right, so that's how we would test this joint hypothesis to see whether or not classroom instruction matters once we've controlled for hours spent studying and major. In our assignments in class, we might do a similar thing where we look at the crops, for example. So in the assignment in class, we're always looking at the determinants of farmers' income, and we have a number of dummy variables, 4 or 5 dummy variables for the different crops. And we might include, let's say we've got 5 dummy variables, and we include 4 of them to avoid the dummy variable trap, and we find that 1 or 2 of them are significant, but the rest aren't. We might ask ourselves, okay, I can see whether or not this particular crop is significant or this particular crop is significant. But do the crops jointly matter? Does it matter for the whole group of crops? Once I control for the amount of education the farmer has and the amount of land they have and whether or not they use fertilizer, perhaps it doesn't matter what crop they grow. So in that case, what I would do is do a joint test on all the different crop dummy variables that I have in my regression model. All right, so these might be some reasons for me to use this joint test, this joint F-test. Okay, so that's the motivation. Now, how do we do it? So we've already had this discussion before. We talked about this model. We talked about why we would do an F-test. We talked about what our hypotheses would be. All right, but now, how do we conduct it? How do we conduct the test? So what happens is that when we are running an F-test, what we need to do is we need to utilize what we call a restricted model and then an unrestricted model, okay? And then we're going to create an F statistic, similar to a T statistic, but in this case it's an F statistic. We're going to create an F statistic, and then we're going to test our null hypothesis using our F statistic and an F table. So it's just like the other one. It's just like a T test, but in this case, it's an F test with an F statistic and an F table and an F distribution instead of a T distribution. All right, I'll get to that in just a minute. Now, how do we do it? How do we construct it? So if we're doing this, what I'll say by hand, that means we're doing it ourselves. We're not using a static command. What we're going to do is we're going to have an unrestricted model and a restricted model. All right. The unrestricted model is just the full model that we want to estimate. So it's all 4 independent variables. The restricted model is the model in which we impose the null hypothesis. All right. So you remember our null hypothesis is that beta 1 equals beta 2 equals 0. Basically, our null hypothesis is that the instructional form that that the student takes their classes in doesn't matter. It does not matter what instructional type they use once you've controlled for hours and major. All right, that's our null hypothesis. And so our unrestricted model is just the normal model, and then the restricted model is where we impose the null hypothesis. That means beta 1, beta 2 equals 0. So if beta 1 and beta 2 equals 0, that means that this whole term is 0, and this whole term is 0, and so then you end up with your restricted model here. All right. Then what happens is that we run both models. You run the unrestricted model and you find the sum of squared residuals for the unrestricted model. Then you run the restricted model, you find the sum of squared residuals for the restricted model. Then you use those numbers to construct your F statistic. Okay? So your F statistic is the sum of squared residuals for the restricted model minus the sum of squared residuals for the unrestricted model divided by Q. Q is the number of restrictions. So in this case, I have 2 restrictions because I have restricted beta 1 and beta 2 to equal 0. All right, so in this case, Q is equal to 2. All right, all of that divided by the sum of squared residuals for the unrestricted model divided by n minus k minus 1, where n is your sample size and k is the number of independent variables in the unrestricted regression model. All right. Now, Q is going to be the degrees of freedom for your numerator. This will be important in just a second. And then n minus k minus 1 is going to be the degrees of freedom for the denominator. We're going to use all of that information in a t-test, looking that up in a t-table. I'm sorry, an f-test and f-table. All right, but real quick first, before we look at the f-table, we compare the how does this work? Remember, when we do a t-test, we figure out, how big is our t-value, and we see whether or not our t-statistic is extreme enough in our t-table to reject the null hypothesis. Okay, well, we do a similar thing with an f-test, but in this case, we're using an f distribution instead of a t distribution. An f distribution looks like this. It's cut off at one end, it peaks really quickly, and then it trails off for a long time on the right end. All right, and what we are looking for is whether or not our t-statistic lies within the critical F region, this F region way out here, this really unlikely region of the F distribution. Okay, but it functions the same way as a t-test. If your F statistic is big enough, you'll reject the null hypothesis. The critical region is determined by your level of significance. If you impose a 1% significant level, then your F critical value will be way out here. And if you impose a 10% F critical value, your F critical value will be here. All right, so it works the same way as a t-test, but it's just using an F statistic and an F distribution. All right, now this is an F table. All right, this is an F table. All right, the way the F table works is you take your F statistic. Let's say our F statistic is, okay, I'm just going to make up a number and let's see what happens. Let's say our F statistic is 3.2. All right, that's our F statistic. Let's just say it. Our F statistic is 3.2. All right, so what we're going to do is we're going to find the degrees of freedom for our numerator. We said the degrees of freedom was 2. Okay, and the degrees of freedom for our denominator. That's n minus k minus 1. All right, so let's say our sample has 300 observations, and then so that's n equals 300. K is the number of independent variables in the unrestricted model. What's our unrestricted model? That's this one. All right, so how many independent variables do we have? 1, 2, 3, 4. All right, so k is 4. So what's the degrees of freedom for the denominator? Well, it's 300 minus 4 minus 1, so it's 295. All right, and the degrees of freedom for the numerator, that's 2, because we have 2 restrictions. All right, so let's look it up. Degrees of freedom for the numerator, 2. Degrees of freedom for the denominator it's going to be 295. So let's go to the nearest number. Let's go to 120, and let's go over here. Now here's this cutoff F statistic value. I said our F statistic was 3.2. If our F statistic is larger than the one that we find, then we would conclude that we are significant at the 5% level. Okay, so this is an F table, an F distribution table for a significance level of 0.05 or 5%. Now, we would have to look up a 1% level to see if we were significant at the 1% level. We'd have to look up a different table, but we could just use this one. All right, so I would come here, degrees of freedom 2. For the numerator, for the denominator, it's 295, so we'll go to the 120. Come over here. I said our F statistic was 3.2. We find this is 3.0718. Ours is larger. That means that we are significant at the 5% level. So then we would say, all right, we have evidence to suggest that the classroom instructional format does matter, and that lecture and online are jointly significant. All right, so that is an F test by hand. Be prepared to conduct an F test by hand in the next classwork. All right, now let's get into heteroscedasticity and let's get into our assumptions. All right, so again, remember, we've got some assumptions. These are the assumptions of the ordinary least squares model. When all of these assumptions hold, then the estimate that we get using ordinary least squares is the best linear, unbiased estimator of the true population coefficient. All right, so if these hold, then we have our estimate, our beta hat is blue. It's the best linear unbiased estimator. So what are they? Conditional mean independence, constant variance, no perfect multicollinearity, observations of the error term are uncorrelated with each other, the error term is a zero population mean, and the error term is normally distributed. Today we're going to focus on the constant variance assumption. This is the homoscedasticity assumption. What this assumption is saying right here is that the variance of the error term conditional on x is constant. That means it doesn't matter what the value is of the independent variables. The error term has the exact same constant, the exact same variance. So the error term has the same variance no matter what the value of the independent variables are. That's what this is saying. That's homoscedasticity. I'll be more clear about that in just a second. All right, if that's violated, then we're going to have problems in our estimation. Okay, like I said before, if all of the assumptions hold, then beta hat, our estimate of the true beta, is blue, best linear unbiased estimator. Okay, so what is heteroscedasticity? What is heteroscedasticity? Let's get into it. All right, so we're talking about the second assumption, the constant variance assumption. This is the homoscedasticity assumption. So homoscedasticity is where the variance of the error term, conditional on x, is constant. So to do this, we need to review variance, and we need to understand the variance of the error term. Okay? So to do that, we need to remember that epsilon, the error term, is a random variable, and it itself has a distribution with a variance. Okay, so let's review. All right, so consider a generic simple regression model. All right, so we've got a dependent variable, an independent variable, error term, and then of course we're interested in estimating the coefficient beta 1. All right, so we estimate this model, find beta 1 hat. We want to know the variance of beta 1 hat. All right, so remember the variance of beta 1 hat. The variance of beta 1 hat is sigma squared, which is the variance of the error term, divided by the total sum of squares of the independent variable times 1 minus r squared, right? We just went over this in the last lecture. Okay, what I want to highlight here is that when we're calculating the variance of our coefficient estimate, we're calculating the variance of beta 1 hat or beta j hat here. If we're calculating the variance of our coefficient estimate, that variance is a function of the variance of the error term. All right, sigma squared is the variance of the error term. So the variance of the error term is in the function for the variance of our coefficient estimate. Then the variance of the error term is going to be very important to us. All right, and that's where this is going to happen. That's where the action is going to happen here. Is what are the implications of this homoscedasticity assumption when we're estimating the variance of our coefficient? All right, so now let's get into, let's just remind ourselves, kind of what the variance is and what it means when we talk about the variance of the error term. And then what's homoscedasticity and what's heteroscedasticity. All right, so we have the error term. We're saying the error term is a random variable with a distribution. Okay, so there's some distribution, and we're saying, based on our assumptions, let's go back for just a second. Based on our assumptions, we're saying that the error term is normally distributed. That means it has that nice, clean, bell-shaped curve. Okay, and the error term has a 0 population mean. All right, so that means that the distribution of our error term, we're assuming that the distribution of our error term is going to look something like this. All right, it's centered at 0, so the mean of the error term is 0, okay, and it follows this nice normal distribution. It's a nice normal distribution, okay, and then it has a variance which measures, the amount of dispersion of the possible epsilon values. All right, and just like before, the larger the variance, the wider the distribution of epsilon is, right? Okay, the constant variance assumption is that the variance of epsilon is constant. Okay, it does not change as the value of the independent variables change. All right, so put differently, we are assuming that each error term is drawn from an identical distribution and therefore has exactly the same variance. So it doesn't matter what the value of the independent variable is, the variance of the error term is constant. It's always the same. All right, that's the homoscedasticity assumption. Constant variance. Okay, so what does that look like? All right, so homoscedasticity is that, so for all values of x, all values of the independent variable, the variance of the error term is sigma squared. That means we have one single distribution. Where the variance of this distribution is sigma squared, and for all the different values of x, epsilon has the exact same distribution. It looks like this no matter what value of x you have. All right, so let's figure out what does this look like a little bit more tangibly. Okay, here I have a scatter plot of, again, income versus education, years of education. All right, so here's all of our data values. Every individual in our data set falls somewhere within this scatter plot. So this person has 4.5 years of schooling and they make $4,500 a year. Or $45,000 a year. Okay. All right. So here's a scatter plot of our data. All right. And so now what we're saying is that for each value of x, all right. So x, our independent variable, that's education. So for each value of x, the variance, that means the amount of dispersion in the error term is sigma squared. The distribution of the error term is the same. Is the same variance. That means if you have 6 years of education, the exact same amount of variance. 8 years of education, the same amount of variance. 10 years of education, the same amount of variance. What does this look like? All right, so let's plot a trend line. Here we go. Here's our regression line. All right, and what I'm saying is, all right, I'm throwing up a distribution here. So this is at 8 years of education. What I'm saying is that the distribution, so right now, I'm superimposing this, I'm superimposing my distribution of the error term over top of my data, all right? So here's a distribution at 8 years of education, all right? And just kind of think about this as being 3D. This is kind of coming off of the screen, all right? Now, and what we're saying is that there's the same distribution of the error term no matter what years of education you have. So here's 8 years of education, and then here's 10 years of education, the exact same distribution. The error term has exactly the same amount of distribution whether you have 8 years of education, 10 years of education, 12 years of education, you have the exact same distribution with the exact same variance. All right? So distribution of the error terms conditional on x. It doesn't matter what x is. It doesn't matter how many years of education you have. There's the same amount of variation in the error term at all the different levels of education. Okay, so that would be homoscedasticity. So this, what I've just laid out here, that's homoscedasticity. The distribution is the same for all the different levels of education. Well, what does heteroscedasticity look like? All right. If the constant variance assumption does not hold, then we will have heteroscedasticity. And so that would be this here. The variance of the error term, conditional on xi, is equal to sigma squared I. So what we've done is we've added this I subscript because now the variance is different for different values of x. Now the variance is going to be different for different values of x. All right, so let's make this more clear. Heteroscedasticity is that the variance of the error term changes based on the value of x. So, for example, let's say that x equals 1. In that case, the error variance is going to be sigma squared 1. Okay, so let's say that's this one here. That's this distribution here. So the distribution when x equals 1 is pretty small. Very small variance when x equals 1. All right. But now let's say when x equals 2, instead of being the same distribution with the same variance, now we have a different distribution of epsilon with a different error variance. All right, so now we've got sigma squared 2. All right, and it's a wider distribution. All right, and then the same example. Let's say that x equals 3. Now for a different value of x, again the distribution of epsilon changes. And so now, and in this case, the distribution gets wider as the x variable goes up. Okay, so now we've got different distributions of the error term for different values of x. All right, what does that look like in practice? All right, here's the data set. Here we have income in Tanzanian shillings, all right, and versus land, the amount of land that the farmer owns. And see if when we look at the scatter plot of the data, we can see some striking characteristics. We can see that there's a lot of dispersion in the data, very large amounts of variance in the data at low levels of land ownership. But when farmers have a lot of land, there's very little variation in the data. So when farmers have a lot of land, there's very little variation. They're all really close right here around the mean. But when farmers have little land, there's way more variation. Look at how much more variation there is when farmers have very little land. All right, when we look at this, we'd say, oh, wow, the variance of the error term must change based on the value of x. The variance of the error term when x, here x is the land, when x equals 10, the amount of variance when x equals 10 is much larger than the amount of variance when x equals 50 or when x equals 55. All right, so we look at this data and we say, wow, the variance of the error term must change. All right, let's fit a line to it. Let's say we fit this line to it. It's our regression line. And what we're saying is that the distribution, the variance of the error term is different for different values of x or different values of land. So when land is 10, it is a very wide distribution with very large variance. When it's 20, it shrinks a little bit. When it's 30, it shrinks a little bit more. When it's 40, it shrinks even more. And so now the variance of the error term is changing for different values of x. When x is large, so when x is around 40, the variance is very small. It's a very tight distribution. When x is 10, it's a very wide distribution. Large variance. Okay, so this is what heteroskedasticity looks like. So this is what homoskedasticity looks like. The error variance remains the same as you have different values of the x variable. And heteroskedasticity is where the error variance has different values depending on the value of the independent variable. Okay. Now let's take a look at what this might look like using these tables and thinking about homo and heteroskedasticity kind of in terms of numbers. All right, so here I have kind of two mock data sets, and in these data sets I have 4 individuals, okay, and I have the same x values 1, 2, 3, 4, 1, 2, 3, 4. Okay, I have the same predicted y, the same predicted dependent variable. It means beta 0 plus beta 1 times x is 4, 6, 10, 13. All right, so these two columns are the same, and these two columns are the same. All right, but now in this top table, I'm going to have something that looks a lot more like homoskedasticity, and in the bottom table, I'm going to have something that looks like heteroskedasticity. So in the top table, my y value is 5, 6, 9, 14, which implies that my error term is, so for the first person, the error term is 1, second person it's 0, the third person it's -1, the fourth person it's 1. Okay, now this kind of looks like homoskedasticity. All the values are pretty similar. It's entirely reasonable to look at this and think that the variance is constant between these 4 individuals. So when x equals 1, the mean is 0, and the variance is probably somewhere around 1. It's probably like a standard normal distribution. All right, and that remains the same for all 4 individuals. They all have very similar values. It'd be reasonable to look at this and think that they have the same amount of variance in the error term. All right, so this is kind of what homoskedasticity would look like. But now here's an example of what heteroskedasticity might look like. So in this case now, my y variable is equal to 4, then 8, 14, and 25. All right, now that translates into an error term where for person 1, the error term is 0. Person 2, it's 2. Person 3, it's 4. Person 4, it's 12. All right, so in this case, we can see that the error term is definitely changing. The variance of that error term must be much larger when x equals 4 than it is for when x equals 1. It's most likely that the variance is much larger when x equals 4 than it is for when x equals 1. And so this is kind of what heteroskedasticity would look like, kind of from a data perspective. Okay, so if the constant variance assumption does not hold, then we have heteroskedasticity. What problem does heteroskedasticity cause? So if we have heteroskedasticity in our model, our standard error estimates, the estimates of our standard error of our coefficient will be biased. This is not as bad as biased coefficients themselves. So we're not saying that the coefficient estimate itself is biased. We're saying that the standard error of the coefficient estimate is biased. All right, so we could say maybe it's not as bad as having biased coefficients. This isn't like omitted variable bias. So it's not as bad as having a biased coefficient, but it's still bad because it makes our hypothesis testing unreliable. So just back, if we think back to our multicollinearity lecture last time, what we found was that multicollinearity caused a problem for our hypothesis testing. Heteroskedasticity is also going to cause a problem for our hypothesis testing. Because what's happening is that if the homoskedasticity assumption does not hold, that means if we have heteroskedasticity, then that is going to affect the variance of our coefficient estimate. And if it affects the variance, then it will affect our hypothesis testing. So what happens here is that if we have heteroskedasticity, our standard error of our coefficient estimate will be biased. And if it's biased, that's going to mess up our hypothesis testing. It's going to make our hypothesis testing unreliable. Remember our t-statistic. All right, and just remember, when I refer to hypothesis testing in this context, I'm talking about the t-test that we run to test the null hypothesis that our coefficient is equal to 0. Okay? And when we do that, like I said, we run a t-test using a t-statistic, and our t-statistic is equal to our coefficient estimate, our beta 1 hat, divided by the standard error of that coefficient estimate. But now, if that standard error is biased, if the standard error is biased, then our t-statistic will be biased. Our t-statistic could be too big or too small. And if our t-statistic is too big, that means we have a greater chance of committing a type 1 error. That means we reject the null hypothesis when in fact the null hypothesis is true. If our t-statistic is too small, that increases the chances of a type 2 error. That's where we fail to reject the null hypothesis when the null hypothesis is false. Okay, so we don't want biased estimates of the standard error because that will mess up our hypothesis testing. All right, now let's drive this point home by reviewing. Remember the variance of beta 1 hat. The variance of beta 1 hat is a function of the variance of the error term. Okay, but we do not observe the variance of the error term. The variance of the error term, because the variance of the error term is a population measurement. We don't have data on the whole population. So we estimate it using the residuals. So this is a review from last lecture, right? So we estimate it using the residuals. We estimate the error variance using the residuals, right? And then once we've estimated the error variance using the residuals, then we estimate the variance of the coefficient estimate. We use that to create the standard error of our coefficient estimate, which we then use in generating our t-statistic. Okay, so what happens is that when we have heteroskedasticity, that will disrupt the estimate of our variance, because now the variance of the error term is not constant. Okay, and so if it's not constant, then we're going to get some biased measurement, a biased estimate of our variance of the coefficient. If the variance of our coefficient estimate is biased, then our standard error will be biased. And if our standard error will be biased, then our t-statistic will be biased. And if our t-statistic will be biased, then we will have a difficult time doing our hypothesis testing. We'll be more likely to commit a type 1 or a type 2 error. So if our standard error is biased, our t-statistic will be biased. That means that our t-statistic will either be too large or too small. If it's too large, it's a greater chance of type 1 error. If it's too small, greater chance of type 2 error. So, in summary, heteroskedasticity makes the estimates of the standard error biased. It does not make the coefficient estimate biased. It does not make the coefficient estimate bias. So this doesn't cause the same problem as omitted variable bias. Okay? It's not making the coefficient estimate bias. It's making the standard error estimate bias. All right? But this makes our hypothesis testing unreliable. That means when we're interpreting our coefficient, or when we are interpreting our regression results, we don't know whether or not we can trust if it's significant or not significant because the standard error is biased. All right, so that will be a big problem. It doesn't make our coefficients biased, but it makes our hypothesis testing unreliable. And so if heteroscedasticity is a big problem, then we need to know whether or not we have it. So let's test for heteroscedasticity. So one of the first things that we can do to test, quote unquote, in this case I'm putting test in quotes because it's not a formal test. We're just kind of looking for it, to get an idea. Again, we always start with intuition and get an idea of whether or not we have heteroscedasticity. One of the first things we can do, if we're concerned about heteroscedasticity in our model, is we generate scatter plots between our dependent variable and our independent variables. So, we write down a model that we think makes sense, and then we produce scatter plots of our dependent variable graphed versus our independent variables. If the dispersion in the dependent variable is rather consistent across different values of the independent variable, then we tend to be confident that we don't have heteroscedasticity for that variable. If it changes a lot, it varies a lot across the different values of the independent variable, then we might be concerned that there will be heteroscedasticity. All right, so just to give us an idea, what does that look like? So let's say that I produce a scatter plot of income versus age, and it looks like this. This is pretty homoscedastic. It looks like there's roughly the same amount of variation for all the different values of age. It's not perfect, but this, if I saw this, I would say, okay, that's homoscedastic. But then let's say we do it for income versus land, and we see something like this. That looks heteroscedastic. Because on one end, there's a lot of variation. So for low levels of land, there's a lot of variation. And then for high levels of land, there's very little variation. All right, so when I look at this, I'd say, okay, this is heteroscedastic, and this is homoscedastic. All right, so here, no problem. No error, no bias in our standard error estimates. Here, very much concerned about bias in our standard error estimates. Okay, and then there's a couple different formal tests. I'm going to show you how to do one of them here. This is called the Bruce-Pagan test. I'll show you how to do another one in Stata. Okay, this one I'm going to show you how to do by hand. The other one, I will demo doing this one by hand and using a Stata command in Stata. And then I'll also show you how to use the Stata command for a different test, for the white test. Okay, so let's talk about the Bruce-Pagan test. So the Bruce-Pagan test, what we do is we run our regression model using ordinary least squares. All right, so let's say this is our model. We've got x1 and x2. And then what we do is we predict the residuals. So we produce the residuals. I'll show you how to do this. Okay. Then we square the residuals. Then we regress the squared residuals on the independent variables from the model in step 1. All right, so we regress the squared residuals on x1 and x2. We keep the r squared from the regression in step 4. All right, and then we use that r squared to construct an F statistic and perform an F test. All right, and so this would be our F statistic, and then we will then go and look this up on an F table. You should be prepared to do this in classwork. All right, where we just plug our r squared into this formula for an F statistic, and then we will look it up on an F table. All right, so those are two tests. We'll do a little bit more of this when we get into the data set. All right. Now, lastly, solving for heteroskedasticity. So what if we have it? What if we have a heteroskedasticity problem? In that case, now we've got to try to solve it. Actually, for as big of a problem as heteroskedasticity can be, the solution is rather straightforward. So a bunch of very brilliant econometricians have shown that we can estimate the variance of our coefficient estimate. We can estimate the variance of beta 1 hat using a different formula, and this different formula will be robust, quote unquote, robust, even in the presence of heteroskedasticity. That means this will be an unbiased estimate of the variance, even if there's heteroskedasticity. Okay? And so what we will do is we will report or calculate robust standard errors. It's called robust standard errors instead of the conventional standard errors. All right. So the standard estimate of the variance of our coefficient is what we've shown already in class. We use the sigma squared hat that's based on the residuals. All right. Then we use that to calculate our standard errors, and then we use that to calculate our t-statistic. But now instead what we're going to do is we will calculate a robust. So this is just a different estimate of the variance of the coefficient, which will give us a different estimate of the standard error and a different estimate of the t-statistic. But in this case, it is robust even in the presence. It's valid. It's an unbiased estimate even in the presence of heteroskedasticity. All right. And so what we do is we just we estimate the variance using this robust measurement, this robust calculation, then calculate the standard error from it, and then use the standard error to calculate the t-statistic, and then we will have eliminated the heteroskedasticity problem. Okay, the way that this is done is now we are calculating it this way. We're calculating the robust variance of this beta j hat, our coefficient estimate, using a slightly different formula. We're using a slightly different estimate of the error variance. All right, we can see it here. Let's break it down. Ui squared is the squared residuals from the regression of y on xj, our independent variable. And then this rij hat is the ith residual from the regression of xj on all other independent variables. All right, and then this is how we estimate. We just use a slightly different calculation to calculate the robust variance of the coefficient estimate. And then we use these robust standard errors instead of the conventional standard errors. And that solves our problem. It's pretty straightforward. I'll show you how to do it in Stata, and it's a very straightforward solution. And the nice thing about robust standard errors is that they work whether you have or don't have heteroskedasticity. And so what we'll see when we do our Stata is that typically what you'll do when you run regressions is you'll just always use robust standard errors, no matter what, because they're valid whether you have or you don't have heteroskedasticity. It's a really convenient solution. Okay, so with that said, let's jump into Stata and get to our demo. All right, so let's open up Stata. All right. Okay, here we go. We got Stata. I'm going to open up wage 4. All right. Use basically the same data set. All right, so let's do lecture 7, heteroskedasticity. heteroskedasticity. I've seen heteroskedasticity spelled different ways. I always spell it with a K, but my word processors, Word seems to think it's with a C, so I'm switching over to spelling it with a C. Okay, now, first, let's specify a model of wages that we think will be a good model. So first, specify a model of wages, right? We always start with theory. So let's do wage equals wage is some function of education, experience, female, and married. Okay, let's say that's our model. And now let's estimate that model. Actually, no. Okay, so first step, specify the model. Second step, do we have heteroskedasticity? Skedasticity. All right. So one of the first ways we can check is just by producing some scatter plots between our independent variable and between our dependent variable and our independent variables. And we're going to focus here on our two continuous variables. All right, so let's just produce some scatter plots and see what we think. Okay, all right, check that out. Oh, that didn't get any bigger. Okay. That looks, what do you think? Is this homoskedastic or heteroskedastic? I think this is a textbook example of heteroskedasticity. There is a tremendous amount of variation when education level is high, and very little variation when education values are low. And it really, it's a textbook example. It's getting bigger and bigger. The amount of variation is getting bigger and bigger and bigger as education goes up. And so that is an extreme amount of heteroskedasticity. All right, what about scatter? What about experience? Okay, this one's a little bit less clear, but it looks like there's a heteroskedasticity as well. It looks like the variation in wages is smaller when experience is high, and it's larger when experience is low. There's a lot of variation here, and there's a lot less variation here. And so it looks like we have heteroskedasticity for both for both education and experience. Now, let's do a formal test. All right, let's do our Bruch-Pagan test. Now, I need to go back and check that spelling. I'm forgetting how it's spelled. All right, definitely misspelled it in multiple different ways. All right, Bruch-Pagan test. All right, so let's remember, how do we do this? First step, run the regression. We run the regression model that we're interested in, experience, female, married, okay? And then what we're going to do is predict the residuals, all right? So this is how we do that. This command here is going to give us the residuals from the model, all right? Step 1, regression, all right? Step 2, residuals. All right, so let's do these two. So here's our regression results. All right, and then I did predict resid and to get the residuals. And here I have a new variable, and it's the residuals from this regression. All right, now I might just pause here for a second. I can look for heteroskedasticity also by producing scatter plots of the residuals versus my independent variables. So let's just take a look at these. The same issue holds here. If we see a lot of variation in the variance of the residuals across different values of our independent variable, then it will confirm our concerns. Okay, so here are the residuals, very large residuals, Very large residuals when there's high levels of education, very low residuals, very high variance in the residuals for high levels of education, very little variance in the residuals for low levels of education. All right, so again, that's just another way of kind of informally looking for heteroskedasticity. You're looking for the same thing. So, okay, here are residuals. Again, yes, very little variation in the residuals at high levels of experience. A lot of variation in the residuals for low levels of experience. Okay, so this looks like heteroskedasticity. Okay, now let's do step 3. We're going to square residuals. All right, so gen resid2 equals resid times resid. All right, so we're going to generate squared residuals. All right, step 4, regress the squared residuals. All right, so we're going to do resid2, regressed on our independent variables, experience, female, married, okay. Boom. Now what we do here is we keep our r squared, so our r squared is equal to 0.2218. All right, so we keep that, and then step 5, we're going to perform an f-test using the r squared. All right, so now let's do that. Let's open up our slides here. Oh, look at that. We are already there. Let's calculate this. Get out our calculator. All right, r squared divided by k. So r squared is 0.2218 divided by the k, the number of independent variables. We have 4 of those. All right, so that is 0. That is 0. I'm just going to type this in here. 0.05545. All right. Now, clear it. Let's do the denominator. 1 minus, all right, 1 minus r squared, 0.2218. Okay. So we 0.7782 divided by n minus k minus 1. Well, what's our sample size? It is 505, okay, minus k, that's k is 4, so it's 501 minus 1, so it's 500. So divided by 500. All right, so there we have that number. I'm just going to type that in, 0.015564. Oh, it's 2 zeros after the decimal. There we go. All right, and so now let's do the division. 0.05545 divided by 0.001556. What do we get? Let's see, did I do that right? Let's make sure I did that right. 0.05545 divided by 0.001556. Okay. Our F statistic is 35.6. That is a very large F statistic. That is a very big F statistic. I'm pretty sure that is going to be significant in our F test. But let's go ahead and do it by hand here. Let's check our F test. What's the degrees of freedom for our numerator? Well, it's 4. Okay, what's the degrees of freedom for our denominator? It's 500. Okay, so we'll be conservative and pick this. This 120. All right, so now 4, take that down, 4 intersects with 120. So here's our cutoff, 2.44. If our F statistic is larger than 2.44, then we are significant at the 5% level. Our F statistic is 35.6. We are much larger. We're definitely significant. That would mean that we have that means we would reject the null hypothesis that there's no heteroskedasticity and conclude that there is heteroskedasticity. All right, so there we go. There we have it. The Bruce-Pagan test by hand, quote unquote. Let's use Stata now. All right, so now we're going to do the Bruce-Pagan test using Stata, using the Stata command. It's pretty straightforward. Wage, EDUC, expert, female, married. All right, and we do EStat het test. EStat het test, that's our Bruce-Pagan test. And the Stata uses a slightly different approach, but you still just look at your p-value. Your p-value is 0.0000, very strong level of significance, and we can comfortably reject our null hypothesis. All right, the null hypothesis is constant variance. We reject our null hypothesis. We have a lot of reason to believe that there is heteroskedasticity. All right, and let's use another test. There's another test. Let's use Stata white test. All right, same procedure basically. Wage, education, experience, female, married. All right, and then we're going to do what's called the white test. Imp test white. I think that's the command. I think there might be a comma here. All right, so we're going to run this. This is a white test, just another test. And here's white test. Null hypothesis is homoskedasticity. Alternative hypothesis is heteroskedasticity. The p-value is very small, and therefore we can safely conclude that we have very strong evidence to suggest that there's heteroskedasticity in this model. We think that there's heteroskedasticity just from our scatter plots. We think there's heteroskedasticity from our scatter plots of the residuals. We did the Bruce-Pagan test by hand. We did the Bruce-Pagan test in Stata. We did the white test in Stata. I think it's safe to conclude we have strong evidence of heteroskedasticity. All right, so now solving it. How do we solve it? Well, if you remember, we use robust standard errors. All right. How does that look like in practice? Well, all we do is we run our regression: wage, education, experience, female, married. All right, and it's really straightforward, comma, robust. In Stata, it's very straightforward. Just comma, robust. All right, so now at this point, what I want to do is I want to run both models. I want to run them side by side. Here's the model with the conventional standard errors, and then here's the model with the robust standard errors. I want to run them side by side. I want to look at them together, and then I want to go through coefficient by coefficient and talk about how heteroskedasticity is going to affect the interpretation of your results, okay? So let's run this model. Here's our basic model. We know that there is heteroskedasticity in this model. We have very strong evidence that there's heteroskedasticity in this model. All right, so before we run the model with the robust standard errors, let's talk about the results from the model that has heteroskedasticity. Okay, let's talk about this. Let's go through it line by line. Remember, I said heteroskedasticity does not cause bias in your coefficient estimates. Well, what are the coefficient estimates? Here are your coefficient estimates. This column here, this column right here, right? Here's our coefficient on education. Here's our coefficient on experience. Here's our coefficient on female. Here's our coefficient on married. Okay, so now we're saying that heteroskedasticity does not cause bias in our coefficient estimates. So if in this situation we are assuming that we don't have omitted variable bias, and let's just assume that for right now, then we would say that this is an unbiased estimate. This coefficient is an unbiased estimate of the effect of education on wages. Okay? And even though we've already shown we have heteroscedasticity, even though we have heteroscedasticity, it does not make this number biased. This is still an unbiased estimate, right? Assuming that in this example. Okay, now that means that when we run our regression with robust standard errors, this number should not change, right? So when we correct for heteroscedasticity, the coefficient estimates should not change. And they're not changing because heteroscedasticity does not affect the coefficient estimate itself. Here's the coefficient estimate. Heteroscedasticity does not affect this. Does not affect the coefficient on experience. Doesn't affect the coefficient on female. Doesn't affect the coefficient on education, right? It does not affect the coefficients. What it does is it causes bias in the standard errors. Okay, so here are the standard errors. Now, because we have heteroscedasticity, we know we have strong evidence of heteroscedasticity for both our education variable and our experience variable. That would mean that when we look at these standard errors, we look at these and we say, okay, these are biased. The standard error is biased. If the standard error is biased, then that makes us say, oh, I can't trust the standard error. This standard error could be larger than the true standard error or smaller than the true standard error. This standard error could be larger or smaller than the true standard error, which means I will have a biased t-statistic. Remember, let's just review. The t-statistic, we're testing. Every time we've run a regression, we test the null hypothesis that the coefficient is actually equal to 0. And the way that we test that is using a t-test and a t-statistic. We calculate the t-statistic. Let me get my calculator out again. We calculate the t-statistic by dividing the coefficient, where it is for education, 8393, divided by 0.030388. All right? And we'll get a t-statistic of 2.76. Okay, that's exactly what we get. All right, so this is where our t-statistic comes from. It's the coefficient divided by the standard error. Get our t-statistic. We use our t-statistic to figure out our significance. So here's our p-value. Here's our p-value. We would look at this result. Okay, we would look at this result and we would conclude that education is significant at the 1% level because the p-value is 0.006. So it's less than 0.01. Okay, so we would look at this and we would say that education is significant at the 1% level. All right, for experience, we would say that experience is significant at the 10% level. But we have heteroscedasticity. That means our standard errors are biased. They could be too big or too small. We don't know. Which means our t-statistics are either too big or too small. We don't know. That means we can't trust these p-values. This p-value would suggest that education is significant at the 1% level and experience is significant at the 10% level, but we actually can't trust it. And that's the heteroscedasticity problem. So now let's go and try to correct. We're going to correct for the heteroscedasticity problem. What we're going to find is that the coefficients do not change, but the standard errors will change, and the t-statistics will change, and the p-values will change. Let's see how they change. So now I'm going to run the model with robust standard errors. All right. So here we've got our two models. This is the one with conventional standard errors. This is the one with robust standard errors. Okay, first you'll notice the coefficients are the same. The coefficients don't change, right? They don't change because heteroscedasticity does not cause bias in the coefficients. And when we use this robust command, what we're doing is we're correcting for the standard error, not anything having to do with the coefficient estimate itself. Now, with robust standard errors, let's compare them. Like I said, the standard error will now be different. So let's look. Here the standard error was 0.030. Now it's 0.03, basically 3, rounding up. For experience, it was 0.006. and now it's 0.004, 0.005 rounding up. Okay. So now the standard errors are different now that we're using robust standard errors, which means the t-statistics will be different. Now, let's look. Let's compare these. Now, in the case, okay, I mentioned before that heteroscedasticity makes the standard error biased. But we don't know whether it's biased up or biased down. It could be biased up. The standard error could be too big, or the standard error could be too small. If the standard error is too small, then we increase the chances of committing a type 1 error. That means we find it to be more significant than it actually is. If the standard error is too small, we find that it is more significant than it actually is. All right? That's what we see happening here in the education variable. Here's the standard error, here's the biased standard error, and here's the robust standard error. The biased standard error is smaller than the robust standard error. Okay, that means that education with the conventional standard error is going to be more significant than it should be. In this case, it's significant at the 1% level. But now, with the robust standard errors, it's significant at the 5% level. Okay? So with heteroscedasticity, education was considered more significant than it actually was. All right? So that's what heteroscedasticity caused for the education variable. Let's look at experience. Again, the coefficients are the same, but now let's look at the standard errors. In this case, the standard error is smaller with robust standard errors than with conventional standard errors. That means, all right, so we know that this standard error is biased. Okay, this one's biased. That means this is biased upwards. That means it's too big. The standard error is too large. It's biased upwards. If the standard error is biased upwards, then the t-statistic will be biased downwards, and we will find that it is less significant than it actually is. All right, so if the standard error is biased upwards, then we will find it to be less significant than it actually is. All right, so we find a p-value of 0.098. That's significant at the 10% level, although it's really close. I mean, gosh, if we made a little bit of a difference, if the data was just a little bit different, you could imagine a scenario in which we would actually say that experience was not significant because of the bias caused by heteroscedasticity. This could be a big deal. Heteroscedasticity can actually make variables insignificant when they're actually significant. And so that would make us commit a type 2 error, right? In this case, we find that it's significant at the 10% level, but we know that it's biased. We know that the standard error is too big. That means we find it to be less significant than it really is. Well, when we correct for it, the standard error is smaller. We've gotten rid of that bias, all right? And now we find a p-value of 0.028. Now it's significant at the 5% level. Okay, so in this example, we have an example of both cases. Education is biased downwards, which makes it more significant than it should be. Experience, the standard error, is biased upwards, which makes it less significant than it should be. All right, so heteroscedasticity can cause a problem in both directions. All right, but now we use robust standard errors, correct for that problem, and now we find education is significant at the 5% level and experience is significant at the 5% level. Okay, so there we go. There's our illustration of heteroscedasticity. I hope you enjoyed the lecture, and I look forward to seeing you in class. Have a great day.